Okay. Okay, so we are now recording, and it's a great pleasure to welcome Kirill his stuff to give today's lecture. He's going to tell us about n equals 2 supergravity in 4 dimensions and Nekrasov-like partition functions. So I hand it over to you, Kirill. His camera, unfortunately, is absent, so so you won't see him in person.
Well, you can see my picture, but hopefully that's also not too important. As long as you can understand what I'm saying, just, well, I can stop anytime, just go ahead with questions. All right, so thanks a lot for the invitation to speak. Yeah, I'll be talking, well, you see the title, but I'll try to at least explain the main idea without going into a lot of technicality. So the main things that you hear are based sort of on this paper by my own and a short, well, it's not exactly corollary, but I guess implication from this conjecture that I'll be presenting. But there's plenty of other things that are related to it. So some new solutions of black holes that I have worked with other people than you see when I speak about gravitational blocks. So I'll try to sort of connect to previous papers as well. And all these papers are in various collaborations. So obviously there's plenty of other people that are involved and have done a lot of things on the subject. So my main message, hopefully it's not going to be very technical, and hopefully you can understand it, is that I will try to argue essentially that the structure of supersymmetric observables in supergravity, 4D n equal to 2 supergravity, has precise analogy to the structure of observables in rigid field theory. So if you would just forget about supergravity and just look at partition functions or correlation functions in 4D n equal to 2 supersymmetric field theory. And this sort of logic, I would even, argue that should hold more generally for any sort of number of supersymmetry and dimension, but of course I will mostly talk about 4D n equal to 2. What I mean here is that, so in 4D n equal to 2 field theory, there's the idea of Nekrasov partition function, which allows you to essentially factorize observables split them into smaller building blocks. And the same idea, I will try to argue that helps in calculating also supergravitational partition functions. So there will be the analogous, what I call Nekrasov-like partition function, which is a gravitational object from supergravity. And the idea is that essentially we use exactly the exact full logic of 4D n equal to the rigid field theory and extend it to supergravity to be able to calculate exactly observables. That is not at leading order in supergravity, that is weak Newton constant, but including all perturbative corrections of higher derivatives in supergravity, as well as there would be a natural extension, including non-perturbative. And I should say here, so I'm saying here that the logic of 4D n equal to 2 supergravity observables would follow from 4D n equal to 2 rigid field theory observables, but of course I'm not saying there is a duality in the standard holographic sense. So what I'll be talking about still has agreement. So the supergravity dual, when we have asymptotically AdS at least gravity solutions, will have holography and will have exactly holographically dual results for 3-dimensional, not for 4-dimensional, n equal to 2 superconformal field theories. So what I mean here is that, of course, the gravity degrees of freedom will be exactly equal to 3-dimensional ones, the 3-dimensional CFTs. However, the tools that we use will be the ones dictated by 4D n equal to 2. So that's the sort of distinction I want to emphasize. It's not that I'm claiming supergravity for the supergravity is the same as for the field theory. I'm just claiming that the calculational tool, that is the factorization in this into Nekrasov partition functions, can be generalized to hold in supergravity. Okay, so this is really the main idea, and slowly I will try to make it very precise. But let me just start with something very sketchy and schematic. This is how the factorization in 4D rigid supergravity, that's not supergravity, but rigid supersymmetry field theory looks like. So just the idea is that one can define the so-called Nekrasov partition function, which is the partition function of the so-called omega deformation background, which is just flat space for C2. In 4 dimensions, one can define these so-called deformation parameters, epsilon 1 and 2. And there's the so-called Nekrasov partition function, which is, there's an exact localization result, if you want, that you can calculate this partition function on flat space, which depends in general on the Coulomb branch parameters in field theory.
Sorry, just to clarify, this partition, this is a non-commutative deformation that you're talking about. If you go to the Moyal plane in C2, associated with C2, that's what the Nekrasov one is, isn't it?
Yes.
Yeah.
But
Okay.
but what I will be concerned to is essentially that. Well, let me go to the next point. The idea essentially is that these full partition functions, let's say of S4, which Peston calculated via localization, or other manifolds, they can be split up into products of the Nekrasov partition function. So these deformation parameters, it's important that you can, let's say for S4 or for any other background, you can actually see, and they would be essentially, you have 2 fixed points of certain isometry, which follows from supersymmetry. And at these 2 fixed points, so the South Pole and the North Pole, you can identify in a particular way, depending on supersymmetry and on the geometry, of course, that is underlying. So here for S4, what is the actual value of these deformation parameters? And the actual value, it just depends on geometry, really, and on supersymmetry. So it's a parameter that can be explicitly evaluated. And the idea of gluing copies of this. So gluing means that at every different fixed point, the value of the deformation parameters could be the different, or they are related in some particular way. So this is in the formula below. This is the general gluing formula. So the sigma is the different number of fixed points. And so at every fixed point, you have these 2 deformation parameters identified that is glued in a different way. And then also in principle, the Coulomb branch parameters might be different or identified in a non-trivial way. For example, it could be that the Coulomb branch parameter on the South Pole is minus or 1 over the Coulomb branch parameter on the North Pole, etc. So, and this idea is actually a conjecture, more general conjecture of Nekrasov that you can prove for S4 by localization, but more generally, it's a conjecture for any partition function in 4D. You can say, or at least the ones that exhibit fixed points under the isometry. So you can deform the S4. You can take much more complicated 4-dimensional manifold, and the idea is that schematically this formula would hold again. So you would integrate over the Coulomb branch parameters and identify in some particular way the geometric deformation parameters, and then you would be able to give. Well, of course, I'm not saying I can solve this in general, but you're given essentially the matrix model, the localization result, this way.
Are you going to explain to us the Nekrasov deformation?
I will talk about it much more in supergravity. So this is just very schematic.
Because
I don't want you. I don't want you to go into to think of the actual details of field theory, because in supergravity there will be a slight simplification, which will mean that only one of these two parameters will be independent, and it will be easy to identify how to get it. So let's go to that part. So the idea in supergravity is that schematically the previous picture would hold again, but of course I will slowly try to make it less schematic and very precise. So the idea is that we need to start with a supersymmetric solution, of course, of supergravity, since we're talking about exact partition functions. I'm going to always assume some secret idea of localization behind, of course, not the idea of Paston, but the idea of Nekrasov, more like. So there will be a supersymmetric solution, and of course, to every supersymmetric solution we can assign, or it comes with a killing spinner. And the killing spinner, when you calculate the killing spinner as a bilinear, you get a killing vector field out of it. So a particular isometry on the supersymmetric background M4. And this is what I will be calling canonical killing vector field. Okay. And so the idea, which to some extent has been shown to hold already, particularly in minimal gauge supergravity at two derivatives, where things are much simpler because you do not have many fields, you just have the metric essentially and one gauge field. So you can show that the on-shell action of a given supersymmetric background, so of M4, localizes on the fixed point set of the canonical killing vector field. Which what it means is that it's just well, the on-shell action is a sum over independent contributions from different fixed point, or of course when we talk about Z as a partition function, which is just the exponent of the on-shell action, it's going to be a product, similar to how it was written in the previous slide. So this idea works, or was shown to work in two derivatives in some examples, but I want to so this is what I will be explaining, how to generalize this idea. So this is hopefully to some extent answering the question of Denjo. So we have the canonical killing vector field, and near a fixed point you can expand it. Of course, near a fixed point will have a flat space R4, which will be parameterized, well, as C2 again. So you can think of two complex planes, and in polar coordinates we'll have two angles, phi1 and phi2. And this is how essentially, by the way, this killing vector field is going to be a U1. So I'm assuming here compact isometry, right? Which for AdS it means I need to take the coordinates where I have identified time. So near a fixed point, generically, there will be some constant or whatever you have that depends on the particular background, epsilon1 multiplying this part, phi1 of the vector field, and there will be another one. However, because, well, epsilon1 and epsilon2 would be exactly, sorry. How did I make this? There's some arrow that shows up on my screen, but I don't know how I did it. So sorry about that. But
that's okay.
In any case,
these things happen.
I really have no idea what I did. But what I wanted to say is that these are the epsilon1 and epsilon2. However, in supergravity, the point is that because we have the killing vector and the killing spinner, they're not in general uniquely defined. You can rescale them freely by an overall constant, because you have well, because supersymmetry is a local symmetry. It's not a global one anymore. So actually, only the ratio of these two parameters is going to be physical in supergravity, and that's the difference with what I wrote before. So the point is that this ratio omega, which I will be calling it omega from here on, will be something that you can explicitly read off from the background. And I will later on, when we start discussing explicit examples, I'll be of course talking about how to read it off. So the main idea now, or what I want to talk about from now on, is how to extend this general idea to arbitrary higher derivative supergravity, including vector multiplets, and give more examples about it. Okay, so this is essentially, this was sort of the small intro that I wanted to start with, and now I will go in a little bit more details about higher derivative supergravity, the formalism, before being able to actually write down the general conjecture, and going later on, I'll go to some examples. So if you have some general questions still, or I will now have to start with a little bit more of technical stuff.
Yeah, I'm not sure I understand the Necrosoft deformation in field theory, because I'm a little bit confused as to how that would work on S4. I thought it was a global deformation in the field theory.
So on S4, you would have, well,
you're going to cut the S4 into two patches, probably.
Yes, exactly. You're going to cut the S4 into patches, and it depends whether S4 is round or what is the metric on the S4. So if you squash it, you have, so you can deform the full. So if you do not deform S4, I think these epsilons will be fixed to be 1 or 0, something like that. You know, they are something that truly depend on your geometry. So if you do not do, if you want to keep the full isometry of S4, I think you are not going to be able to have meaningful parameters for these deformations. They'll be probably
I mean, S4 doesn't have a complex structure, and there's no way of...
I think you can. I think you can still probably squash it in some. So you can break the isometry probably to some extent. I will.
Okay.
Because I will be giving examples of S2, and there I am. It's
S2 has no problem with. Yeah. Okay.
Yeah, it's much easier to know how to squash the S2, and I'll be reading off the omega there. But
okay.
Essentially, the fast answer is that if you can somehow introduce some deformation parameter of the full sphere, so if you can squeeze it or squash it somehow, it will end up being respectively the epsilon1 and epsilon2 will depend on that geometric deformation. If not, they will be fixed to some canonical value that is 0 or 1, something like that, which would essentially correspond to the round sphere. So you wouldn't actually be able to see these deformation parameters carrying much information, but they will be there in some sort of trivial way that would still make sure the full answer for the partition function makes sense.
Okay,
that's what I'm saying.
Sure.
We'll see actually that some values for the omega are very special and will simplify a lot the whole calculation. So I'll talk about that as well.
Okay, I will wait.
Right. So let me just try. I'll try to do it as fast as I can and without a lot of complication here. But I need to talk a little bit about higher derivative supergravity. So the idea of for the n equal to 2 supergravity is that you need to first increase the symmetry to the superconformal group, which allows for much easier classification of higher derivative terms. With, we're talking about derivatives that are more than 2 derivatives in the classical, in the Lagrangian, which from string theory point of view will correspond to corrections, right? So there'll be quantum corrections to the coming from string theory compactification to the derivative effective action. And essentially these terms can be simply classified in terms of, well, they can be F terms, which correspond to chiral superspace integrals, which would be essentially, you can think of them as holomorphic quantities, so being captured by holomorphic function, and the terms from full superspace integrals that will correct the Kähler potential. That is, it will not come in a holomorphic way, but in a real way. So it will have both parts, holomorphic and anti-holomorphic. But the D terms are something that will argue and can be argued for all the examples that I'll be talking about, that they have to vanish. So it's really only the F terms that will be playing an important role here. And there, well, the whole formalism is somewhat complicated because you need to introduce a lot of auxiliary fields and auxiliary multiplets that, due to having extended sort of by hand the symmetry, and those ones you have to introduce them to be able to write down the full higher derivative invariants, Lagrangians, but then there is a consistent procedure to come back to Poincare supergravity. And one important assumption here, I'll be talking about theories where the hypermultiplets, so there could in principle be charged scalar multiplets, and I will not be discussing them because they come with a different type of higher derivative corrections, which I'll be won't be discussing, which would in principle correct the hypermultiplet, so the quaternionic Kähler manifold, which is set by the hypermultiplet. So I'm only talking about vector multiplets, so abelian vector multiplets, whose higher derivative corrections are captured by F terms. And just so that you get some sort of intuition about explicitly the multiplet, there's the gravity multiplet in superconformal formalism is called the Well multiplet and has the metric. It has auxiliary gauge fields that become on shell, just become the R symmetry, U1 times SU2. Then there's an auxiliary tensor and scalar. There are vector multiplets that need to be the usual. You can choose NV, free number of vector multiplets, but you need to add one auxiliary one. And then they also come with each of them comes with some auxiliary scalars. But importantly, the complex scalars that are physical and gauge fields will, of course, remain. And then one has to introduce one auxiliary hypermultiplet. So even though we are not allowing for physical ones, we need to add one auxiliary hypermultiplet that is going to allow us to gauge some of the R symmetry. So we can choose either. I'm going to talk about both ungauged supergravity and gauged supergravity. And the gauge supergravity will be such that we gauge a subgroup of the U2R symmetry via free combination of these parameters, which are called Eliopoulos parameters. And I'll be explicitly talking about two different F-term types. Here I have written 4 derivative F-terms. They are 4 derivative off-shell, but they will be infinite derivative on-shell. So even though when we write them down in the Lagrange, in the off-shell Lagrangian, they are just 4 derivative terms. In fact, because they're defined by these composite chiral multiplets with the scalars, which are the lowest components, they're actually composite scalars that will relate to the physical scalars via derivatives. So we'll see that on shell the power of these AW and AT will give us also the number of derivatives. Let me make this very precise. The whole Lagrangian is actually captured by this holomorphic prepotential object. So it depends on the physical scalars, complex scalars X, which are in the vector multiplets. But then it depends explicitly on the AW and AT, which are responsible for the W and the T invariant, what I call W and T invariant, or more precisely, Weyl squared and T log in these two papers. And so you have this infinite expansion in principle in powers of AW and AT, where
I missed something. I understand what Weyl squared is, but can you say again what T log is?
It's another invariant. It's another invariant that you can write. It's a more recent invariant. It's in general less known and less studied in the literature, but it's very similar in the sense that you can again write down. You can uniquely define the Lagrangian of this T log using the lowest component of the composite multiplet that you're using.
So it's a geometric invariant on the manifold.
No. It's so it depends explicitly on well, these are composite fields AT and AW that depend on all the other fields in some particular way. I didn't write it explicitly, but they depend via derivatives on the complex scalars, on the gauge fields. So it's an invariant that captures the whole. It's a true invariant of the theory that is not geometric because, of course, it does include R squared sort of invariant, or R mu nu, or R mu nu rho sigma squared. So it includes geometric invariants, but it includes many more terms.
Yeah, and it doesn't have a it doesn't have a non-supersymmetric
topological meaning on it,
or geometric meaning, because Weyl is the leading theorem, and I know what it is. It's just the reduced part of the
yeah, exactly. So this one, just the metric, the curvature part of the Weyl squared invariant will be related to the Gauss-Bonnet term, and so there will be some topological part of it when you evaluate it. However, because of supersymmetry, this comes with many other terms that have derivatives on scalars, derivatives on vectors, and of course derivatives on fermions, etc. So the
leading term for the T one is much more complicated. It involves other matter fields automatically. Is that the statement?
Yes.
Okay.
But it also involves R squared, I think, but it involves R squared in a way that is multiplied by extra scalars.
Okay.
For example, so I don't think you can easily think of it purely geometrically.
Okay.
But of course, it might depend on your definition. Maybe some parts of the invariant would be something that you can easily spot what they should be, but I don't have this definition intuition, let's say. So the leading term here, or the one that has no AW and AT powers, is just two derivative prepotential. So it's a function that is fixed by supersymmetry to be homogeneous of degree 2, and it gives well, as long as you also specify, of course, the Fi parameters, the gauging parameters, it specifies uniquely the two derivatives Lagrangian, and then all other terms here, they're also fixed by supersymmetry to be of particular degree. So they are homogeneous of degree 2 of 2 times 1 minus m minus n. So negative degree as you increase the weight of AW and AT, and it gives rise to higher derivatives in this way. So the whole thing is very well, it's very constrained essentially. So you don't have well, supersymmetry does that for you essentially. So you can of course, within this constraint, there's infinitely many functions that you can write down, but hopefully you'll see in some ways we can fix that indirectly, unfortunately, because the best thing would be to have a string theory compactification that just lends you with these values, which we don't have. So let me go down now to actually writing down the conjecture. So the conjecture is that downhill action of any four-dimensional background that exhibits fixed points can be written as a sum over the different fixed points. So these sigma are the fixed points, and the sum over, well, sum which is weighted by particular signs depending on the chirality of the Killing spinors, but apart from this technicality, it's a sum over these building blocks that are essentially entirely fixed by the prepotential, where, remember, the prepotential in the way I wrote it is, function of the scalars, and then there's the AW and AT. Here in this formula, AW and AT are evaluated to be equal to 1 minus omega squared and 1 plus omega squared, where omega was the what I started with. It's the deformation parameter. So it's the parameter that you can track down from the canonical killing isometry stemming from the killing spinors. So essentially what I'm saying is that the deformation, the geometric deformation, that you can just read off from a particular background, dictates the entire higher derivative expansion. So these two, essentially the AW and AT, being fixed in terms of omega, means that as long as you know the geometric deformation, you know the entire higher derivative expansion, formally, at least. Of course, for an explicit answer, you need to actually know these functions here. But the expansion in terms of AW and AT of the higher derivative invariant is dictated by the geometric deformation parameter. And extra stuff that we need to know and comes with it's called the so-called gluing rules, is how you identify at these different fixed points the scalars x, which would, again, just like in rigid field theory, depend in general on Coulomb branch parameters that we'll see what they are later on, and on the geometric deformation as well. And these are, I don't have a general rule on how to, it sort of makes sense when we discuss different examples that there's some sort of pattern maybe emerging, but I don't have an explicit way to tell you how these gluing rules come. And there is one additional constraint, I should say. So somehow there's always one parameter too many in the parameterization that I'm using, which has to be restored, because really one of these parameters is it's not a physical parameter, because one comes from actual auxiliary vector multiplied. So let me just mention here that already when you look at this formula, you can notice that omega equal to 1 and omega equal to -1 are two special values that are going to simplify things a lot, because if one of these is 0, so one of the AW or AT is 0, it means an entire tower, a huge sum in principle, an infinite sum, collapses to nothing, to 0. So there are these special, very special values of omega that would simplify a lot the calculation, which I will be calling unrefined limit and Nekrasov-Shatashvili limit. This simplification is the same, also happens in rigid field theory as well.
Just one further thing with the number of spaces or space-times with killing spinners. Is that countable? It seems like
this is a hard question. I don't think so. I don't think there's a.
I'm just wondering if there's a classification of how many. I mean,
there is a classification for certain type of killing spinners. For example, time-like ones that lead to the canonical isometry being time-like. But again, it depends a lot on the underlying supergravity. So in minimal supergravity, when you don't add extra vectors, I think there's classification. But then also, sorry, it depends on whether you're in Euclidean or Lorentzian, of course.
Yes.
I didn't mention this, but in Euclidean, there's more solutions. And I'm allowing here, I'm going to allow Euclidean. So I'm claiming that these formulas should make sense as well for Euclidean, not just for Lorentzian supergravity.
Okay.
So okay. I think in some restricted sense, there is classification, but it's not not entire classification, and certainly not in a way that you can say they're countably many.
Right. So your sum had a sum over.
So the sum is not over geometries. It's just a sum over fixed points of a fixed geometry. I'm just take one your
fixed
favorite
geometry, and they at the fixed points you have killing spinors.
So what tells me is that if I have a supersymmetric geometry, it comes with a killing spinor, of course.
Exactly.
And this killing spinor, when you square it, you get a killing vector. Right?
Yes.
Now this killing vector, it might or might not have fixed points on the geometry, right? In principle, it maybe rotates or translates the geometry in some way.
Sure.
But there will be some special points that are fixed.
Mm-hmm.
And these special points are the ones that contribute. And there will be very few of them. In the examples I will give you, there is 1 or 2 fixed points.
Okay.
I know some examples where you have 4 maybe fixed points, but it's in general there's not a lot of fixed points.
Yes, that's what I was expecting. Okay, all right,
yes.
and that's consistent with there not being a lot of possible supersymmetric geometries consistent with that background.
Yes, maybe this is another way of saying this. So let me just say that I'll be talking also about black holes, and for black holes, some of these parameters, what I call Coulomb branch parameter and omega, they have a natural interpretation in the grand canonical ensemble of these black holes, because they come with the conjugate variables, so the chemical potentials of electric charges and of rotation of the angular momentum. So in these black holes solutions that I'll be partially discussing, some of the main examples will be black holes. We'll have also a natural way to go to the microcanonical ensemble. So just Legendre transforming the on-shell action, and this way we also recover the black hole entropy. With the standard, you have to extremize this function also, so that you go to I'm sorry. You go to the microcanonical ensemble, and there you have a sort of another constraint instead on the electric charges and angular momenta, which is resulting from the constraint I mentioned on the chemical potentials. So this is also a way, this proposal gives a way to evaluate the black hole using higher derivatives, the black hole entropy. But furthermore, another thing that follows from this conjecture is that you can put it in a path integral. Essentially, down-shell action is just, you can think of it as the leading term of the partition function, of course. And a natural conjecture that follows is that even if you have extra corrections that do not follow from supergravity, essentially the supergravity result, as I will show you the examples, but the statement is that it factorizes on different fixed points, and it is natural to conjecture then that the whole UV complete answer also factorizes. So instead of just the supergravity answer, the supergravity partition function, supergravity on-shell action factorizing in terms of these building blocks depending on the prepotential, we can say that there's conjectural general Nekrasov partition function, which would be the UV complete answer, that is some extra corrections to the supergravity answer, that would also factorize. So the same gluing rules would give you, as long as you can identify the whole UV corrected block, would give you the full answer for the complete quantum corrected. So not only higher derivative corrected, but also fully quantum corrected with whatever string theory tells you apart, that is more than supergravity in general, Kaluza-Klein states, and so on. And this, here it is completely abstract, just a proposal that the same factorization takes place. But I will give you an example where it is just explicit. So we'll see that this proposal can be made explicit in some special cases, of course. So again, I realize, I hope it's not too technical, but I realize I cannot present it without giving these technicalities about the deformations and about the higher derivative terms. So if you have questions, I will try to now make things much more explicit by discussing some examples, and hopefully starting with the simplest examples as I'm going further. So hopefully, just the main message is that I'm not doing much anything too different than the standard for the rigid idea of Nekrasov that is factorizing the building blocks. However, I'm giving a very explicit proposal for what these building blocks are in supergravity, and of course they are not. This is not related in any direct way to field theory. So this just depends a lot on the supergravity details, which is the prepotential given by this Weil squared and T log invariants higher derivatives. Okay, so if you have questions, I will now try to go to examples and maybe make it more explicit for you.
Okay, I'm looking forward to the examples.
So the simplest example is just asymptotically flat black holes. It means we are not considering any Fayet-Iliopoulos terms. We just have asymptotically Minkowski solutions, and these are half BPS flows in principle between Minkowski, and there's the near horizon geometry AdS2 times S2, which actually by itself is also fully BPS. So it preserves all supersymmetries. It's just literally AdS2 times S2 with equal radii. And this is the near horizon of standard asymptotically flat black holes. And there it is, you have the killing spinors explicitly there, they essentially, because it's AdS2 times S2, or you have, of course, the full flow, the full killing spinors. You can easily, find the canonical isometry, and it exhibits two fixed points. So the idea is that, well, you can just think of the canonical isometry as it's a dt, the time direction, plus d phi, where phi is it's minus dt plus d phi, where phi is just one of the two angles on the sphere. So you can see easily that from the point of view of the full flow, but also from the point of view of just looking at the horizon, the two fixed points are at the horizon. So there is no fixed point of this isometry anywhere in the full flow in the bulk outside of the horizon. They're exactly at the horizon. The tau has a fixed point at the center of AdS2, and then the phi is just fixed at the two poles of the sphere. Otherwise, it's an equatorial translation. It's the rotation along phi. So you can see that only the south and north pole of the sphere are fixed under phi. They do not move. And therefore, you just have exactly 2 points that are fixed. Of course, it's 4-dimensional thing. So it's the center of AdS2 times the south pole and the center of AdS2 times the north pole. That are the two fixed points, right? And there you can actually see, but you can already see it here, that the geometric deformation parameter, which we defined as the ratio of the two factors in front of the two parts of the killing vector, is just -1. And furthermore, just for completeness, there was these two signs that were in the factorization formula that are aligned with the chirality of the killing spinor. So you can see that at the fixed points, in general, the killing spinors are not of definite chirality, but they become of definite chirality exactly on the fixed points. and they're of opposite chirality. So at the south pole they're of positive chirality, and at the north pole of negative. So if we now we have the geometric deformation, and however we also have something that is known for ages now. These are the attractor equation, the so-called attractor mechanism. So we know how the scalars are fixed at the horizon, and we know exactly how the entropy behaves. So we know that the way to find the attractor mechanism, that the scalars are fixed in terms of electromagnetic charges, and actually the entropy in well, it's given by the so-called OSV formula for Ugovi-Strominger-Waffe. So they propose that one should do it in a mixed ensemble, which means the magnetic charges are fixed, but the magnetic charges are traded for their chemical potentials. So in this way, they wrote down the formula. This is at two derivatives for now. So just without any corrections, it's the prepotential. Well, you can already see that even though they did not write it explicitly, the formula looks already like a factorization or a sum of two parts, the formula. And if we apply the conjectured formulae for the particular deformation I wrote down with these gluing rules, so I need to, as I said, the extra thing that I need to give you is the gluing rule for these scalars x. So notice that there is a flip of signs between the south and north pole identification. But if I do that here, I'm just going to write it without justification, as I said. But we'll see that all the black holes exhibit sort of well, that is all the black holes, including AdS black holes as well as Minkowski black holes, have this sort of gluing. Then you end up with the exact same OSV formula. However, the only difference is that in their formula, I'm just using a different normalization for what I call the Coulomb branch parameters. However, everything is the same at two derivatives. And moreover, everything works also in higher derivatives because we do know exactly the full higher derivative on-shell action. It's particularly easy for the following reason. Well, of course, there's infinitely many higher derivative terms, but I'm saying still particularly easy because if you notice, there was omega equals to -1 for this case, which is exactly the unrefined limit. So in the general formula, we had the Weyl square invariant being proportional to 1 minus omega squared, and then the T-log invariant being proportional to 1 plus omega squared, but the 1 plus omega squared actually vanishes because omega is -1. So infinitely many terms in this higher derivative expansion are identically 0. And because the near horizon is fully BPS, one could actually solve this completely. And in this case, actually, this formula, that the way I wrote it is slightly different, but it matches exactly the OSV formula. It's proven. It's just proven already in the end of the 90s. So here I presented the general formula as a conjecture. Here it's not a conjecture. It's just true. It holds. And furthermore, it was important to write down this formula because then via further OSV conjecture, this was related to the topological string on the internal Calabi-Yau. So one could actually identify explicitly the higher order, higher derivative terms in the prepotential in terms of geometric data, like these are the Chern numbers of the internal cycles on the Calabi-Yau, et cetera, et cetera. So I don't want to give too many details here because it's an old story, but my general point is that the conjecture holds exactly true. It's essentially already proven 20 years ago. But this is an important example that illustrates the idea behind behind the general conjecture. You'll see that the other examples will be a slightly more complicated version of this OSV formula. So now that we have done the Minkowski case, I want to move to AdS4. There, the details are a little bit different. So instead of here, before we had some string theory on Calabi-Yau, here we have 11-dimensional supergravity. So this is the simplest case that I'll be discussing. So it's the 2D supergravity that actually comes from a truncation of n equal to 8 of maximal supergravity in 4D, which follows from 11D on S7. So here we have exactly 3 vector multiplets. So in total, these 4 complex scalars. The Fayet-Iliopoulos terms are non-zero, so that they generate scalar potential. And therefore, we have the vacuum has a negative cosmological constant, so it's an AdS4 solution. And in the fully BPS AdS4 vacuum, one can show that well, the solution is just that you have equal scalars equal to 1/4, let's say, in some normalization. But what we'll do is that we now discuss the Euclidean version of AdS4. So this it's not important for the empty AdS4 vacuum, but it's important for the generalization. So if you choose an S3 boundary, so if of course AdS4 needs to be Euclidean so that you have a boundary that is compact, right? You don't have time. Then you have generalizations of this solution where you do have radial flow. You have S3, but the S3 boundary gradually shrinks. This is sort of the interpretation, and this is a half BPS solution. And this solution, which is just a sort of generalization of the S3, you can again evaluate. Well, you can find the killing spinners. You can evaluate the canonical isometry, and you will actually find that you have a single fixed point. So here, unlike the black hole examples, you just have the center of AdS4 because you don't have something like a non-trivial topology inside in the book. You just have AdS4 that, well, with the shrinking S3 if you want. But the idea is that here you can exactly find, as long as the S3 is round, so you haven't squashed it, you can find that the deformation parameter is 1. And then because this deformation parameter is 1, not -1, but 1, it actually corresponds to the exact opposite limit of the black holes that I discussed in Minkowski. So it corresponds to the limit where the Weyl squared invariant is 0, but the T-log invariant is non-vanishing. So of course, the prepotential itself is different because it comes from a different string theory compactification, but strangely or maybe coincidentally, this example, even though it looks different, it's from the point of view of the higher derivative terms, it's the precise opposite of it in terms of how the higher derivative structure works for the unshell action. And this is just in agreement with the so-called F-extremization of the dual field theory. However, I should say this is here so far, I'm just talking about the two-derivative case for F-extremization, but I will be now generalizing it to more derivatives. So one thing that we can do on top of this background is to add squashing to the sphere. So this squashing is standardly comes with this squashing parameter B, which happens to be precisely the omega deformation that you can track down from the killing spinner is just equal to B squared. And then if you do have this free squashing parameter, you're in a much more complicated situation because you no longer have this simple limit where one of the two higher derivative invariants vanishes, you have a full, so this is a sum over both the Weyl squared and the T log invariant, and none of them vanishes. So this case where you, well, you just added a single squashing of the sphere to this general asymptotically AdS4 background, but you get a much more complicated answer. And this was this formula that is here really conjecture, because I haven't proven that this must hold, is indeed true. Is if one can show that this is true for if you strictly restrict to 4 derivatives, but this formula is much more general, I should say. And one very nice thing in this case is that there are a lot of exact results known in the dual-field theory, because the dual-field theory is ABJM, so it's just the theory of M2 branes on well, flat space essentially, and there are many papers, so you can just do exact localization in 3D. Many papers that evaluated this partition function, the so-called round or squashed S3 of ABJM. And this allows us to get a match. So what do I mean here is that all these papers, they have, you know, we have this general.
Sorry, just to clarify, you mean you are putting ABJM on a squashed tree sphere? Is that what it means?
Exactly, on this thing, on this squashed S3 with there is for the tree sphere, there is exactly one squashing parameter B. So you break the isometry to U1 cross U1 from you know, so forth.
Okay. Yes, okay. So
sorry,
that's the squashing.
I should say exactly one squashing parameter that preserves supersymmetry. So of course, the more you you want to squash and do things to the sphere, you will break symmetries, and so there is one squashing parameter if you want to also keep supersymmetry.
Yes, I mean there's one natural squashing parameter which takes it into a cigar-like shape. That's
yes,
probably the
I
one
don't
you're
know,
using.
some people call it ellipsoid, or I don't know how you imagine it best, but
yeah, sure, an ellipsoid, yeah, that can be, okay, right. And that's the one. And but it's not quite ABJM that you're using. It is this non-commutative deformed ABJM because of these parameters. They have these Necrosoft deformations.
So I'm not here, right? I'm in for ABJM. I'm not doing what I'm doing in supergravity. I'm just what I mean is that here this is just the ellipsoid, the squashed S3. I don't care how they calculated it. In fact, they calculated it via localization, but they did not use in 3D because it's a 3-dimensional solution. You do not pass through this factorization calculation, or not in this way. In 3D, you can factorize the partition function in different objects, which are called holomorphic blocks.
But you do introduce these epsilon parameters into the ABJM.
No, not
you
really.
don't.
What I introduce is this B, the squashing, but
which is just the temperature.
It's just a geometric parameter. It does not correspond to non-commutative.
Okay, very good. Okay, very good.
So I'm not doing anything very drastic, and in fact, this is it has been exactly evaluated. There's this Fermi gas approach by Marino and Futkov.
Okay.
And so they well, not in the most general case, but in some particular limits of the squashing, you have an exact answer. Right. And this is exactly enough for me to match it to this form of the prepotential. So what I'm saying is that because of these explicit answers and holography, I can now give you an exact answer for the prepotential with infinitely many derivatives.
Okay.
So this is where this piece captures all the higher derivatives, where these coefficients that only they are by supersymmetry fixed to be functions of degree 2 in X. Well, this is a long term. You can read it off in the paper, but it's not important. The point is that in principle they're very tractable and sort of simply looking expressions. So I remind you, the square root of x1, x2, x3, x4, x0, x1, x2, x3 is just the original two derivatives prepotential, and then all the hard derivatives are captured here. And because of the symmetry, they are completely symmetric under permutation of any two indices. Because the four scalars, you can think of them as from the compactification on S7. They're correspond to breaking the SO8 in U1 to the 4, and they're completely interchangeable. And the only thing here is that these coefficients, which are just numbers coming at every different level, they're given in terms of what seems to be the natural quantity in ABGM is this n, the rank of the gauge group in ABGM, and k is the Chern-Simons level. So it comes in an n minus k, where I should say, of course, that the 2D supergravity is valid at large n. So everything comes here in as a Taylor expansion in large n, which you can resum and then get this sort of exact answer. But again, these coefficients, they're very specific because they sort of come as Taylor expansion of every term is suppressed by essentially the Taylor expansion of.
And you believe this formula is valid for any n, right down to 0?
Yes, this is for well, the 0 is easy, the infinity.
Yeah.
Yes.
Okay.
So yes, the statement or the belief is that this is true to infinity. But the good thing is that it can be resummed, because these coefficients are exactly the coefficients of the 1 over 3k in the limit 3k is in the limit 1 over 3k is small. So essentially, this thing, when evaluated on the particular background, when using this omega, so when using this formula, can be resummed exactly. So this infinite sum collapses essentially to this thing, you see? So let me again show this formula, right? So if I'm using this, the on-shell action, or this is minus log of the of z of the partition function, and I feed this explicit prepotential, then I just end up with this answer. So this is the n minus k over 24 minus b gets resummed to this precise formula. There's an overall prefactor c that depends on the squashing, and then it's just this n minus k minus a subleading term essentially in n, because it does not depend on n, but it depends on. So here what I did is that I went to the field theory parametrization, which depends on these x, what the supergravity parameters, just as a 1/2. This is just for an easier comparison with field theory literature. And this answer, which is now entirely found from, well, it is from matching the prepotential with explicit holography, but it gives, because the prepotential is much more restricted a priori because of the various restrictions on the degree of the functions in the prepotential. Now this answer is consistent with this Airy function, so it's the expansion of the Airy function, but it is something that generalizes all the non-localization answers. So even though it was obtained by matching with the non-localization results, this answer is more general than that, because it is valid for any squashing parameter b and for any value of these essentially in field theory they're understood as 3 R charges or masses. of the scale of the, well, the chiral multiplet scalars in ABJM theory. And before it was known that it is an airy function, but it was not these coefficients C and B were not known in their full generality. They were known for specific values of the squashing B and for specific values of the deltas. So there are various limits that you can take and show that this formula agrees with field theory localization. And so what I should say here is that, remember I told you in the beginning in the conjecture, this is the supergravity answer, and it is expected that it gets corrected. There's some UV completion that supergravity cannot capture. And indeed, well, in the next slide or in the slides, you'll see what is the full expansion of the Derived function. I didn't write it here, but this is the leading term, and then there are subleading corrections. And these subleading corrections from the Derived function are supposed to capture all the information that supergravity does not capture. But this is by far the leading term, so supergravity, already gives you all the knowledge that you need to complete it to Derived function, because it gives you these coefficients C and B, essentially. But let me now, since I'm anyway.
Sorry, was the statement when you go back to the previous one, this sum here, this gives an airy function? Is that these coefficients that you?
So this sum here ends up being in this function. So it really gives the tree, because you can think of it essentially as the Taylor expansion of n minus k over 24 minus b around small b. So if you resum this thing, you will end up with this value, with this 3/2.
But where is the Kähler function in the previous expression? As it was meant to be exact.
Sorry. So in this expression,
isn't this meant to be exact?
This is meant to be exact, but notice that, so it is exact, but of course it comes with, look at how it comes with powers of n, right? So for every extra power of n, this is more and more subleading, right? Yes. So if you assume that we are at large n, well, if you assume essentially that these terms are smaller than n, you can resum them into an exact Taylor series, because all these, so you see this is at n equal to 0, this is, you get just the first coefficient.
Yes, I understand. So you're saying that if I choose some additional structure from this sum, I can pull out an airy function?
No, not yet. I'm only saying that you will get to this part, and Derived function. So let me just give you you see the asymptotic expansion of Derived function. Yes. So it is exponent of what, if you look at AI, not BI. So there's two airy functions, but looking at the first one, it's the exponent of minus 2/3 z to the power 3/2, and then there's infinitely many corrections, but they're extremely suppressed with respect to the exponent. If you have, z that you assume large. So I'm saying that supergravity gives you the z, gives you the leading term, and then you can identify the full airy function by knowing that supergravity gives you the leading answer. So the only thing you need is the z, if you want, because supergravity gives you the z, gives you this expression, and as long as you know z, then well, because of localization in ABJM, you know that this resums, the whole answer is airy function actually. So I'm using this as an input from field theory, but really I'm happy enough to be able to identify from supergravity this leading thing, right? So this is what I get here from this infinite sum in supergravity. This extra bit, I'm saying that it should come from the UV completion, whatever it is, because I don't understand how to calculate
Okay.
Well, essentially it comes from Kaluza-Klein modes, you can say, right?
Okay.
So because the supergravity answer cannot be the full answer in
yes,
full
I understand. Okay. All right.
So I'm saying essentially that supergravity tells me this, and all the extra Kaluza-Klein modes should come with in a way that it completes the leading exponent to an array function. However, because this term is enough to give me it's enough to give me the argument of the array function. So there is nothing free. I know that whatever the UV completion is, and no matter how one should calculate this in gravity, it should sum up to array just because I know that field theory gives me that. So
yeah,
theory tells me that it's
but the previous result was the field theory. That sum was the field theory, wasn't it?
So yes, however, yes.
So this includes the UV completion.
It does not include it because I have only I cannot. So I have taken only the terms in the field theory calculation that I can identify with supergravity, right?
Oh,
so
I see. All right. Okay.
So I don't have the full the full way to identify the complete answer in field theory just because I only have supergravity. Or I'm working with this object, the prepotential. So the field theory answers are enough to fix for me the prepotential, but they have more stuff in them.
Okay, I understand. Okay, thanks.
However, the real point here is that still I'm doing something more than field theory because supergravity fixes for me these coefficients due to the additional restrictions on the prepotential in a way that field theory cannot. That is, supergravity fixes for me these C and B in terms of all the parameters. And this is enough for me to also give the full argument of the array, even though I cannot get the array itself, but only the leading term. However, the leading term is enough for me to tell you what C and D are. Okay. Let me very fast mention how this generalizes to other asymptotically AdS4 solutions. So this was just AdS4 sliced in S3 coordinates, but you can do more in AdS4, of course. So you can look at different black holes as well. And one type of black holes are the ones with a twist. So you, in a particular way, you have to switch on magnetic charges for the black holes. You can, again, switch on rotation, where the rotation, the geometric deformation omega will relate to the chemical potential of the rotation. And again, come up with the same gluing rules that we had before. And what you get here is essentially because you have two fixed points. These are, again, similar to the example. They are the center of AdS2 and the south and north pole of the sphere, because you have on your horizon geometry AdS2 times S2. What you get is that because at each separate fixed point, you get the contribution is an array function. Now, for these black holes, you just get two array functions, so a multiplication of two array functions, where now the exact details of the array functions, the arguments depend on the gluing. So these two array functions depend on different, of course, related, but so they're all related. Both array functions depend on the deformation parameter related to the rotation now. This is, you can also think of it as squashing of the S2 now instead of S3. You have so these are the chemical potentials to the electric charges. I'm again using here field theory notation, and these they're related to the magnetic charges. So essentially, I've just converted to field theory notation, but the whole partition function, which is in this case called topologically twisted index, depends, and this is the explicit prediction for it now from the, well, of course, in supergravity, one gets only the leading terms of these both functions, but I can now, because of knowing the gluing, I can extend them to the full answer. And this is, however, sort of complicated and unfortunately not known exactly in field theory. However, there is, fortunately, in this case, there is one nice, very nice limit, which is the static limit. So you're allowed to actually switch off the rotation in this general solution, which means you are allowed to take the limit omega equals 0. And you can see, of course, that when you take omega equals 0 in a particular way, things will be much easier. In fact, they are much easier. So you can see that because of the way you have the multiplication of the two functions, you will not get some divergences, but all the terms depending on omega will cancel out. So what you find in this limit omega equals 0 from the exact asymptotic expansion of the functions is this expression. So it's much simpler expression than the previous one with two functions, but it's still in principle an infinite, well, there's a sum, but my point is that in terms of a Taylor expansion in large N, there will be infinitely many terms here. You can still write them in a closed formula like that. What is nice is that there recently have been numerical results. So they're not analytic as in the previous case, but of course you do know here the ABJM matrix model. And even though there are no known yet fully analytic ways to go beyond large N in evaluation of the matrix model, you can put it on a computer and get a very, very high precision. So actually precision of order something like n to the power minus 10 or something like that. So it means a large, already you can get a lot of the structure, indeed, the full structure. So actually in this paper, they just wrote down the same answer independently, which is a very strong indication that this factorization in terms of array function works, because this is these expressions are not haven't shown up before. They're rather complicated. It's easy to take them to the large N limit, so just forget about all subleading terms here, and you can find the expression in the literature. But with all these subleading terms, that was not it was not available before, and these results are, what I wrote down here, it is completely independent from this calculation. So somehow the fact that they agree is quite amazing, because it means, unlike the case of the square sphere where I compared with field theory, this is it's an expression that comes once I have, essentially this expression comes for me from the conjecture, relating to some of the results for the squashed partition function of ABJM. But this one a priori has no relation at all with the topologically twisted index. So this result, although related to the squashed black hole holographically, is an independent prediction for the topologically twisted index. And let me very briefly say that there's another type of black holes, the ones without a twist, and the mechanism, the gluing mechanism for them, they are again exhibiting similar near horizon geometry. The gluing is similar but not the same. There are some differences in signs and in constraints. So what you get actually is a similar expression, but you actually have both factors of the array function is of the first kind of array function. And here, unlike for the previous black holes, you don't actually have a static limit. So you cannot take the limit where rotation vanishes, because the object itself disappears. There is no such black hole. You can take the so-called Cardi limit, which corresponds to taking a very small omega, and this corresponds to actually you sort of decouple the magnetic charges. They become subleading, but you get another sort of simple expression. However, this one is not yet cannot be tested yet because there is no similar result in the literature for the superconformal index. So these black holes correspond, the ones with no twist correspond to the superconformal index, while the ones with the twist of the previous slide corresponded to the topologically twisted index. So this is just to show you that this sort of factorization happens also or is predicted to happen from the general conjecture also for the other black holes. So let me summarize, because I already went a lot of 20 minutes after
that's okay.
time.
We are
so my general what I hope to take from this is forgetting about the technicalities is just the general idea of using the the field theory structure of observables, the factorization in terms of Nekrasov-like partition function to be able to predict, conjecturally, however, but in some cases very precisely predict the full perturbative expansion of the entropy or on-shell action, and including the UV completed answer for supersymmetric partition function in gravity. And it's something that gives very explicit answers holographically. So we already have some of the, many of these answers that I wrote down are testable, but not yet tested via holography, via the ABJM partition function. So in principle, now one should check, hopefully, that they are correct. So even though it's a conjecture, it's a conjecture that can be checked both using explicit matrix model holography localization techniques. And of course, one should, in principle, also try to prove it within gravity itself, using, in principle, higher derivative, the full higher derivative Lagrangian. But of course, it's rather technically complicated to evaluate infinite derivative Lagrangian on a particular background. But there's many things that are to be done. So I said the gluing rules are sort of, I give you the gluing rules, but I haven't derived them in general for an arbitrary background. And then there are many other sort of examples that can be covered or should be covered of supersymmetric backgrounds. I didn't mention, but in principle, there could be examples with fixed two submanifolds and not fixed points. And these would be slightly different, but should in principle follow from similar rules. So one should also think about them. Of course, I should say also that in principle, what I wrote in for higher derivatives is answer that includes two particular infinite derivative invariants. There could be other. So there is no full classification, even from the point of view of just the type of higher derivative terms we can write. There could be other. However, at least in the ABJM example, it doesn't seem like one needs more terms to get to the full answer. But in other cases, there could be. Then another important thing is to be able to just derive the prepotential not from holography or from some other trick, but just explicitly from string theory, from compactification, which I don't know how to do now. We just know the two derivative prepotential. And these general ideas can be extended for more general theories in 4D, but as well as to other dimensions, because, in principle, the main logic did not have to depend on the explicit dimension. So of course I'm more used to and know much more about 4D supergravity, and then it was easier then for me to borrow some some ideas from 4D rigid field theory, but in principle, one can do it in two dimensions, or 3 dimensions, etc., or 5 dimensions, 6 dimensions. There, one can expect to have similar sort of factorizations, and one can borrow similar ideas from field theory. And well, maybe one can prove somehow ideas CFT at least for the supersymmetric observables using this conjecture. So that's it. Thanks a lot.
Oh, very good.
I don't know how to pronounce this this word in Irish, but
yeah, it's pronounced mille buíochas.
Okay.
It means 1,000 thanks, lots of thanks. But very good.
So yes, thanks for
Agus mille buíochas did féin. Okay. Many thanks to you. Thank you very much for an insight into this this emerging field. Are there
I'm sorry, it might be at some point a bit more technical, but I hope I tried to also emphasize the less technical part of it.
Okay, no, that's fine. Are there questions, or? Then I will thank you again, and I'll stop the recording. We can be less formal.
Yes.
Say so.
Maybe you're the one.